Hey, how are you? How's the research going?
It's going good, getting to learn a lot about physical optics actually.
Oh, very good. Physical optics is fun.
Yeah. Also, there's this another course, 6116. Probability of passing through any space semester is less. But if it does, then it has a lot about.
What course is it?
It's antenna theory, something.
Oh, advanced?
Yeah.
61, yeah.
6116, yes.
That sounds fun. Is it Ellingson going to teach it or who?
Yeah, I mean, if it passes, we might be teaching it.
Okay, well, that sounds fun. Next semester, coming up.
Yes. There will also be like 5106 as well.
5106, yeah.
Handling both and research might be very big. So I'll have to be.
Yeah. Well, hopefully you pick either one. You should probably pick your advisor's course.
I mean, I had a conversation with him yesterday about it, and he did say like 5106 is like necessary to build the basics. So maybe like, and also like there are chances that it might not be offered in the next semester and also. I only take 5106 for sure.
Hopefully you guys will all be prepared for that now that you're taking this course. What is the prereq to it?
I'm sorry?
What is the prereq for 61?
I don't think there's any prerequisite for that.
Okay.
But, I think 4114, it covers like 20-30% of 4114.
Okay. Good. Very nice. So, man, how are you?
All right, how are you?
Good. Figure out those homework problems?
We got that one.
Good.
Stuff on the last one. Last one's tough.
Yeah. It's all algebra though, right?
Yeah.
At the end, but it's algebra with special functions, so you're unfamiliar. Oh, Lord. You're going to be in 5106, right?
I did. I like it.
Oh, yeah?
Yeah.
You've taken it before?
Yes.
Are you gonna be in the next one for?
I want to sign up, but I know like semesters will be really busy, so I might have to sign up for the asynchronous one.
If you've taken it already, you probably can't, right?
I might order it, like I'll
Oh, yeah,
probably
yeah.
sign up for the official one.
Okay. Oh, very cool.
But that was a good chance.
Oh, yeah, yeah.
Yeah.
Yeah, very nice. Okay, so let's get started. It's 9:30. Welcome to the last lecture of the course. This lecture is not going to be included in the material that you're tested on for the final because it's above and beyond what was included in the course objectives. But I thought to include it because you guys deserve something fun and interesting at the end of all the hard work you've done this semester. So we're going to go over metamaterial and metasurface modeling today. And this hopefully will get you excited in some of the newer frontiers in electromagnetic theory that will allow you to push forward and do research in this field. So before we get to that, I want to bring up a few things. The homework, so you should have turned in your project yesterday. If you haven't, then get it to me today by email. All right, and it gives you 5% extra on your final score in the whole course. So if you got 85 after you tallied up all of your points, then you can get a 90, right? So it's super important to do that project. It's worth a lot. Let's say you take the final and you get, an 80 on it, which would translate to maybe a 20% or so of your final grade. Then you would get 100, right? Because you get that extra 5%, or however that works out. It's 5% towards your final grade. All right. And there's a homework due on the day of the final. Make sure you have it turned into Canvas or bring it to me, a physical copy, before or at the start of class here on Friday. The final exam is on Friday. It's a 2-hour exam and it starts at 7:45 in the morning in this room. All right. Everybody who's registered for the face-to-face has to be here to take that exam. There are only 4 people, I think, that are remotely registered. They will take the exam in the same way we did the midterm, where it'll upload to Canvas, a couple of minutes before the exam starts, and you'll have, the 2-hour period to do the exam, and then you must upload your solutions within 10 or 15 minutes after the end of the close of the exam period. So you must prepare to have a scanner near you at the end of the exam if you're a remote student, and to be able to scan your exam fast enough to get it into the submission portal before the deadline closes and the portal closes. All right. Okay, the exam itself is going to have probably 2 long problems and a small quick problem. All right. So you'll have probably about an hour each long problem if you really work it out, right? And when I say long problem, they're similar to the problems you've been doing for homework. So if you can do a homework problem in an hour, then you'll be fine. And the homework problem, or sorry, the exam problems, I'm going to send an announcement today. I'm going to make it easy for you guys. I'm going to send an announcement today telling you what the general topics will be for each of those 2 problems. So I pretty much help you guys out a lot because then that narrows your studying, right? So I'll tell you exactly what to study for the 2 big problems, and just come prepared for that. Last time I told you for the midterm that it was on generalized coordinates, and it was, right? So I'll send an announcement later today because I haven't made the exam. I'm gonna make it today, and then I'll send you some hints on what to study. All right. So come prepared on Friday, early in the morning, for a 2-hour final exam in this room, and you have to be here physically if you're a face-to-face registered student. All right. So make your accommodations to be here. All right. Okay. Any questions on the end of the course? All right, good. Okay, so since it's a bonus lecture, I'd expect maybe half of you to probably be off studying and the other half to be here. But the ones who did come are going to get some exciting material today. So what I've tried to do is I've tried to set this up in such a way that we walk through how we model metasurfaces, right? And metamaterials at the end, but I don't think we'll get to that. But how do we model metasurfaces and define what a metasurface is, right? And there's a lot of new research coming out that has to do with the area of metamaterials and metasurfaces that allow us to do a lot of things we thought were difficult or, were maybe not achievable or not achievable in such a high efficiency manner that we can do today, right? So very interesting things with these models that we're going to develop today. The field's been around since, the first paper that surmised or hypothesized that there was negative refraction was in like the 60s. And then there was a lot of work in the late 90s by Pendry and Smith, who did some realization. And experiments. And then in the early 2000s, a lot of work by Tretyakov and some books. And then my PhD advisor, like in the mid 2000s, or he was working on it too in the late 90s and stuff with his theses. But anyhow, it's been around for, let's say 23, 25 years. Metamaterials. Metasurfaces started becoming popular in the 2010 and above, right? So, but arguably people were developing these models. The models that we're going to go over today were developed in the late 90s, early 2000s. But that's a lot newer than classical antenna theory, right? A lot of the antenna theories were developed, in the mid 20th century. All right, let's push forward. Yeah, any questions? Okay. So I've been piecing these notes together, so they're not maybe as clean and complete as the ones we've been studying before, but we will return to this topic, probably the first topic we study in 5106, but in much greater detail over the course of a few days. All right, so here's a little introduction. Okay, so let's get some preliminary stuff that we already studied this semester. We need to understand the concept of polarization currents, all right, because we're going to use those to model metasurfaces. So here, we already studied this slide, right? This is a repeat from lecture 2 that we studied earlier in the semester. We have an oscillating electron cloud around a nucleus. So the nucleus is the positive part of the atom. It is the red dot. The center of the electron cloud is represented by the blue dot. And when an oscillating applied field excites this atom, it stretches the electron cloud away from the nucleus. And it does that back and forth, right? So that constitutes a current. There is charges in motion, and charges that are being accelerated radiate. These are bound charges, though. They're not free to flow. They're bound to the atom, but they are able to displace, right? We modeled a material that consists of such atoms using the following: the polarization P, the polarization density P. So, and we also defined the electric flux density as epsilon naught E plus P, right? So this is the background field, the applied field, plus the field due to the material. And we can define a new field D that accounts for the field due to all of these polarized atoms, right? And we call it D. Okay, if you then go to Ampere's law, which has the right-hand side a bunch of currents, we have J omega D. We can plug in what D is, and we can distribute this J omega. We get the impressed electric current sigma E, which is the conduction current, the loss, right, or sigma into E, and J omega epsilon naught E, which is kind of the background displacement field. And then we have this term, J omega P. So we have the polarization that varies in time. The polarization field P, which varies in time, constitutes a current, just like this, right? It's a term on the right-hand side of Ampere's law. Therefore, it contributes to radiation in the form of a source. All right? Okay, so, and then I alluded to these earlier in the semester, these two boundary conditions. We're going to derive these today. Hopefully we get to these. But this lecture, we're going to derive these and make use of them. And what we see is it's a boundary condition, right? What are boundary conditions? They link the discontinuity in the tangential components of fields or the normal components across an interface between two dissimilar media or some kind of interface containing material properties or currents, right? Mostly currents, right? So here, delta E is the difference in E on the two sides of the interface. So this is Z cross E2 minus E1, for example, or Z cross H2 minus H1, which we've seen in relation to the other boundary conditions. But instead of having, say, J on the right-hand side, we have J omega P now. So a time-varying polarization field gives rise to a discontinuity in H, just the same as a surface current, right? But then there's these additional terms where we have the transverse gradient of the magnetization, magnetization, which also gives rise to discontinuity in the tangential components of H. And we have, of course, the J omega mu M, which is the time-varying magnetization. We're going to study that in the next slide. All right, so you remember that. Here's the time-varying magnetic current density. So we do the same thing. Recall what we did before. We have J omega P. But here we're going to look at Faraday's law. Curl of B is minus J omega B. And we define B to account for the magnetization of a material as mu naught H into M. So let's substitute that in. We get minus J omega mu H and minus J omega mu naught M as another current, right? This is a time varying magnetization, and that gives rise to a electric field that rotates about it, right? Okay, so remember these terms. We have a current, j omega p is a current, and minus j omega mu m is a current. All right, good. So what are metamaterials? I think we've seen this slide before, but metamaterials, if we define metamaterials as man-made materials comprised of structures whose electromagnetic properties are deliberately engineered to offer a range of response difficult or impossible to achieve in naturally occurring materials or composites, right? So here we have a salt of sodium chloride or a crystal of sodium chloride. If we zoom in on some part of it, we see it's made of atoms. And if we zoom in even closer, a periodic arrangement of atoms. If we zoom in even closer, we see that these atoms have a structure of a particular type of lattice, right? Cubic, face-centered cubic, body-centered cubic, and so forth. And when light interacts with this piece of matter, we don't see these individual atoms, right? Unless we had X-rays or something where we could do X-ray diffraction or crystallography. But here we see, instead we see this, right? So that means that when we illuminate this with wavelengths which are much longer than these atoms are on the order of an angstrom. Visible light, for example, which this picture might have been taken in, it has a wavelength of 600 nanometers, right? So it's 1,000 times longer than the length of an atom, the wavelength of the light that's illuminating the matter. Therefore, we can't see the individual atoms. Instead, we see the average response of all of them together, right? Okay, so that average response gives this material its properties. So maybe what we can do is we can exploit the same properties and design matter illuminated with a much lower frequency than optical light with a long wavelength. And we can arrange some meta atoms now in a periodic arrangement such that we don't see the individual meta atoms, right? We illuminate it with a wavelength at least 10 times longer than the breadth of a meta atom. And instead we see the average response, a bulk material property. So we don't see this granularity, right? It's sub-wavelength. We see the average response as a continuous medium. And each of these meta atoms can be different types of materials, right? We can design these. These are big enough for us to manufacture. And each of these can be designed such that they endue the material with some unique properties that are not normally found in nature, right? So for example, this chiral material or this chiral meta atom here couples the electric response to the magnetic field or the magnetic response to the electric field. So you can start to get unnatural coupling, right? And by exploiting these, by designing these meta atoms in such a way and arranging them in a periodic lattice and illuminating them with a long wavelength, we can design material properties, the bulk continuous material properties, to have negative index of refraction, for example, negative permittivity, negative permeability, or dispersion, frequency response, or time varying properties, or anisotropy, inhomogeneity, or nonlinearity, all kinds of things, right? We can engineer materials now, man-made materials that have tailored light-matter interaction, whatever we want. That allows us to go above and beyond what's normally done in electromagnetic theory, right? So we can do this at an interface level. So that was a bulk material, right? So we have to have wave propagation through the material in order for the wave to acquire the new properties. And if the medium has a little bit of loss, then that wave has to travel all the way through that medium in order to undergo the wavefront transformation. And therefore, the losses might be too much or too great, right? So instead, what we can do is do everything at the interface level, at a boundary. We can derive a boundary condition, have a two-dimensional layer of meta atoms, and this two-dimensional layer of meta atoms will transform the wavefront as it transfers or transmits through the interface, right? And we can derive a boundary condition linking the tangential fields or the discontinuity in them, E plus, E minus, H plus, H minus, to the material properties, the average bulk material properties that we'll derive of the metasurface, which is constructed from these meta atoms, right? And that boundary condition is here. We'll derive that in this lecture. If we get to it, hopefully we do. All right? Okay, so let's start simple. Let's start with a metasurface which supports electric polarization only. All right? So here we have a metasurface made of dipoles. These are vertically oriented dipoles, right? they respond to a vertical incident electric field. If I have an electric field illuminating this metasurface that's vertically polarized, then currents will flow along this dipole arm, and then they will start to go out along these circular arms. Once they reach the gap, they stop, but this gap has a tunable length, so you can increase the capacitance, right? Why are we making these arms on the dipole? We can make it smaller, right? To make it resonant, because this path is now much longer, and it can be made, a longer path can be made resonant at a particular frequency at a smaller geometry, right? And we can tune the capacitance here by making this arm longer. It can extend inward. So this thing responds electrically to vertically polarized incident fields, and it is a electric dipole. It's modeled with an electric dipole. These are small in terms of wavelength, so they respond as electric dipoles, right? Why is it a displacement current, right? Because remember, if this was a metal sheet, then and we had an incident plane wave that was vertically polarized, a surface current would exist, and it would flow along the length of that metal, right? But here we have finite extent for each of these metallic structures or these meta atoms. So the current can only go here and then stop, and then it goes the other direction and has to stop. It has finite support and it oscillates back and forth, exactly like that polarized atom, right? The nucleus and the electron cloud, it stretches away. It's bound to that geometry, right? Bound to the atom. It oscillates within the domain of the atom. Here we have current that oscillates within the domain of the meta atom, all right? So you can't describe these with, I mean, of course, we will come up with a surface current that describes it, but these things are better described using the concept of polarizability and a polarization field and so forth, right? Same as we model dielectrics. All right. So the first thing we're going to study is an infinite uniform array illuminated normally with a single electric field component vertically polarized, all right? How do we calculate the scattered field from such a metasurface? Well, once we have a current, we can do anything, right? We're done with the problem once we have a current, because we know how to calculate the radiated electric and magnetic field due to any current distribution now. We learned that in this class, right? So if we had a current, we can calculate the scattered fields or the radiated fields due to those currents, right? So we can define a current as j omega p, like I said earlier, right? J omega p, and p we can define, what is p? Remember, what was p? P was, very good, polarization vector. It exists within the material. What were its units? Or what did it represent? I don't know if you remember. Is the number of dipole moments per unit volume, right? It's a continuous smearing, if you will, or converting a discrete sum of dipoles into a continuous function that represents the average number of dipole moments per unit volume at that point, right? And I can define that at every point by taking a unit volume, counting the dipoles, and saying at that point, that's the number that I'm assigned to this continuous vector field that I'm going to define, right? So I've converted a discrete sum into a continuous function. So P is the number of dipole moments per unit volume. We're gonna do the same thing here, but we're gonna define it, since it's a surface, as the number of dipole moments per unit area. And we know if we take this unit cell as our, say, unit area, if you will, then the number of dipole moments in that unit cell is 1, right? It's the dipole moment. So dipole divided by a squared is a P, right? Polarization field. One dipole moment, the dipole moment of these atoms. These meta atoms will have a dipole moment, right? We'll study that next. The dipole moment divided by a squared. Okay, but to do that, we have to calculate the dipole moment now, right? So how do we calculate the dipole moment? All right. To do that, we're going to have to define the concept of polarizability. So a lot of this stuff that I'm presenting today, I've taken from a couple of references that are always going to appear at the bottom of the slide. So if you are interested in any of this, you can go to these references and dig deeper, all right? Mostly Tretyakov and Duhun Kwan and some stuff from my previous postdoc advisor, Anthony Gerbic. But polarizability, we got to define first, right? So polarizability usually refers to the tendency of matter when subject to an electric field to acquire an electric dipole moment in proportion to that applied field, right? So here's the definition. polarizability is this proportionality constant alpha. I apply an electric field. We'll find out, or we'll define what local electric field means, but it has to be a local electric field. I apply in a local electric field, and that meta atom acquires a dipole moment. Now, how big or how strong is the dipole moment given a particular local electric field? That depends on the meta atom's polarizability, the proportionality constant, all right? Electric polarizability is the relative tendency of a change or of a charge distribution, like the electron cloud of an atom or molecule, to be distorted from its normal shape by an external electric field. All right, the polarizability alpha, in this case, we're going to start off with an isotropic medium, is defined as the ratio of the induced dipole moment P of an atom to the electric field E local that produces this dipole moment. All right. All right. So a lot of this lecture is going to be about how to calculate this local electric field. It's not as straightforward as you might think. The local electric field, E local, what is it? It's defined as the sum of the primary source field, the illumination, the incident field, and the secondary source fields scattered by the entire array except for the dipole under consideration and evaluated at the dipole under consideration's location. So for example, if I go back to this, if we wanted to find the dipole moment of this atom here, we would have to add the incident field to the field scattered by all of these, every single meta atom. We have to account for all of them because the incident field is going to induce a current here, right? Which is going to radiate, and it's going to couple to that. The incident field will also excite this atom. That will then radiate to the meta atom under consideration. You do not include the scattered field of the meta atom under consideration onto itself, right? Because when you illuminate this metasurface of the plane wave, for example, a current will be induced in the meta atom under consideration, and that current will re-radiate, and that radiated field will then impinge back onto that atom itself and change its current. It couples to itself, all right? And that contribution is excluded. Okay, so remember that. We'll define it more formally, all right? Okay, so having said that, in the case of an isolated meta atom, the local field is equal to the primary source field. E local is equal to E incident, right? There's no other meta atoms, and we're going to use that concept to calculate the polarizability of an individual meta atom, all right? Okay, so let's do that. All right, so you guys solved the wave equation in spherical coordinates in this semester by re-deriving a new form of the wave equation using the vector potential framework. Remember, for spherical coordinates, we couldn't separate the vector PDE into 3 independent ODEs or even one independent ODE. They were all 3 coupled to all 3 field components. So we had to resort to the vector potential approach, and we derived a wave equation in the vector potential framework. We solved that one, and we only got TE to R, TM to R modes out of it. We could only solve for R-directed components. Okay, there's another way to solve the vector wave equation in spherical coordinates, which I'm going to teach next semester. It'll only take a couple slides, but that way, that's classically done in like Mie scattering theory, where you define these M and N functions and you take the curl of them and so forth. All right, there's another way to solve the spherical wave equation, but you get the same functions in the end. You still have to solve homogeneous Helmholtz wave equation in spherical coordinates. And we did that. So you get the spherical Bessel, spherical Hankel, you get the associated Legendre polynomials, and trigonometric and azimuthal functions. All right. So you've done enough to understand exactly what it is. I just didn't want to bog you down with it right now. Why is that useful? Why am I talking about that? Because what you can do is you can expand any field in terms of these spherical mode expansions, right? And I probably could have written down with the spherical mode expansion. I started to do that, but I thought that it's gonna be too much to get the point across. So just know that you can take any electric field in spherical coordinates and you can expand it in terms of what are called spherical modes. And this is a spherical mode expansion. Very similar to what we were doing with the sphere when we solved the sphere last lecture. Okay, so I've only listed the one function that we're going to use for extracting the polarizability. All right. So how do we extract the polarizability of these little meta atoms? These things, right? So I jumped ahead. This is we're going to extract the polarizability of those. And we're going to do that using this approach. So everything is a little dipole, infinitesimal dipole. Remember that. Everything's modeled as a little dipole. Electric dipole only in this case. The far field radiated by a z-directed infinitesimal dipole of length delta z and current I. So it has length delta z, it's carrying current I. It's placed at the origin of the coordinate system. We derived this in lecture 6, I believe. E is equal to I delta z over 4 pi, j omega mu e to the minus j beta r over r sine theta theta hat. All right? Far field. Okay, since we know j is equal to j omega p, there's only one meta atom now, so it's just j omega p, right? The dipole moment is equal to I delta z, or you can rewrite this equation as I delta z. J is equal to I delta z, and then j omega p z. All right? Okay, so a time-varying dipole moment is a current, right? It's the current of a single meta atom. We can rewrite this as E equal to j omega p z. That replaces I delta z over 4 pi j omega mu e to the minus j k over r sine theta theta hat. All right. Now what did we do? We multiplied this j omega here, so we got minus omega squared. And we have the mu pz over 4 pi, right? All right. Well, omega squared mu is almost k squared, right? Because k is omega squared of mu epsilon. So we can say that if we multiply this expression by epsilon, then we'd have k squared here. So we divided by epsilon and multiplied by it. And then we use the one we multiplied by to generate k squared, yeah? So we have this expression. This is going to be useful for us because there's a very similar form of this expression when we consider the spherical mode expansion of the radiated far field due to a dipole. And that's what we're going to do next. So remember this equation. Now, this far field can be expanded into spherical modes using a spherical mode expansion. And the book that you can look up for this is, you can either go to this paper where I got a lot of this lecture from Doohan Kwan, Design of Single Layer Dense Metasurfaces on Irregular Grids using Discrete Dipole Approximation. He did a lot of work that we're gonna learn about today. Or you can go to the book Hansen, Spherical Near Field Antenna Measurements. This is a good book, but it does a lot of spherical mode expansion and stuff. All right. If you come to the next class, 5106, next semester, we're going to study all this in detail. All right. Okay, so E now expanded in terms of spherical modes for a dipole, right? For a dipole in the far field, an electric dipole along the z-axis. It has to be a dipole along the z-axis. We get this expansion, K times the square root of eta, Q 2014. I'll explain what that is. These are indices that describe the spherical modes that are part of this spherical mode expansion. All right. For more information, you got to go to this Hansen reference or come to the next semester's course. But and then F4201. So for this course, this lecture, I just want you to know that F4201 is equal to this function here. All right. This is part of the spherical mode expansion. You would sum over, I think this is S, M, and N, and then this is called C. So this superscript 4 just tells you, is it a Bessel function? Is it a Y function, a Bessel Y, or a Bessel J? 1 is Bessel J, 2 is Bessel Y, 3 is HN1, inward traveling, and 4 is HN2, outward traveling, right? We know it should be outward traveling, so we have 4 for the superscript, and 201 just tells us that it's the only mode we need to describe the radiation due to this dipole, the far field. Okay, anyhow, so we take this k squared of eta. This is a coefficient, it's a complex coefficient. We sum over S, M, and N, and this is just a complex coefficient of the expansion for each term. And we have this function F2014, and we can multiply all this out. We get Q2014 times all of this, right? All right, equate this with the dipole, the known dipole fields analytically, right? If you do the equation, or if you do the equality, equating the two results and using the definition P equal to alpha E, then we can say E here, which is this expression we know for a dipole analytically. We can say that okay, so if we multiply both sides by, or what did we do? Oh, we solve this for PZ, sorry. This equation here, we solve for PZ, all right? Then we get this expression, right? We know P is equal to alpha E. So we take E theta now, and we substitute in our expression for E, right? In terms of the spherical mode expansion. Then then we say then we multiply all this out, right? There's some things that'll cancel. Sine theta will cancel. Then we have it ends up being j squared of 6 pi eta times epsilon over k squared into Q2014. All right. So the dipole moment P of z we've written in terms of this unknown coefficient multiplied by this coefficient as well. And we know that P is equal to alpha E. So we can then say that we can define what alpha is in terms of this unknown coefficient, right? Using this equation down here. By comparing, right? So this is alpha E local. So if a single dipole is illuminated, if the single dipole is illuminated, isolated, and illuminated by a unit strength plane wave, then we know at the point where the meta atom is, at the origin, the phase is 0, because e to the minus jkz, for example, or e to the plus jkz. But z is equal to 0 at the origin. So that exponential goes to 1. So it just picks up the strength of the plane wave. If it's unit strength, then the E local is going to be equal to 1. E local is equal to E incident for an isolated meta atom. So this goes away and everything else is alpha, right? So now we've calculated the polarizability of any meta atom that can be modeled as an electric dipole in terms of this unknown coefficient of a spherical mode expansion. How does that help us, right? We need to determine this coefficient. There's a software called Phaco that does method of moment analysis, and you can use Phaco to calculate. You can draw this geometry in Phaco. Then you can illuminate it with a plane wave, and you can calculate the scattered field, and you can check a box in Phaco that tells you it'll calculate the spherical mode expansion of the radiated far field for you, and it gives you all the coefficients for any geometry. But if you just put a small meta atom there, and you run the simulation for a plane wave of this geometry by itself in free space, you calculate the far field, Phaco will give you the spherical mode expansion coefficients of that far field, right? And what you find is only one coefficient in that expansion. It gives you a bunch of them. Most of them are 0. The only coefficient in that expansion is Q201. So you get that from Phaco for any meta atom. Okay, so I wrote some code, did some Phaco simulations and sweeps, and I put the code here. And here is the polarizability extracted for this particular meta atom as a function of this radius. So what are the defining properties of this? It has a gap width, W. It has a conductor trace width, W. And it has a radius, A. So as I increase the radius, everything changes, right? W is a function of A. Oh, I didn't put that, did I? Oh yeah, here. W is equal to A over 5. So as I scale A, the radius or the circle, the thing gets bigger, and the radius, the conductor trace width scales accordingly. All right, here's A. I swept A from 2.4 millimeter to 3.6 to 10 gigahertz, and I illuminated this as a plane wave, calculated the far field in Phaco, extracted the Q201 coefficient from the output file that Phaco generates, imported it into MATLAB as these two files, and plotted the polarizability. So here's the polarizability normalized to the free space permittivity as units of meter cubed, and yeah, here it is, right? So here's the real and imaginary part of the polarizability. Okay, good. So it's a complex number, right? Great. All right. So now we have the polarizability, but that's only the part of the story, right? Now we got to consider a dense array of dense periodic array of small particles with period A by A. So the unit cell size is A by A, illuminated uniformly so that all particles and their excitation are identical, meaning that this is an infinite array. They're equally spaced. We illuminate it with a normally incident plane wave, so any element is going to respond exactly the same as any other element. They're all the same, right? If you illuminate it normally, and it's an infinite array, and they're equally spaced, and they're all the same atom, uniform, right? All right. To calculate the scattered field, one needs to determine the induced dipole moments, as we said, right? So the induced dipole moment is equal to alpha E local. We just calculated alpha for a given meta atom using software. You can also do analytic. There's the analytic models you can use to calculate the polarizability of particular meta atoms. If you look in Tretyakhov's book here, Analytical Techniques in Applied Electromagnetics, that book has a bunch of calculations, and a lot of this lecture is taken from there as well. Okay, so go there if you want to read more about this. We need to determine the local electric field. So the local field is defined as the incident field plus the field due to all other particles in the array, excluding the particle of interest. Say the particle of interest is that one. Then, and this metasurface is made up of these types of metaatoms. Then the local electric field is the incident field plus the re-radiated field, or the secondary field, radiated by all other atoms in the array, infinite array, by the way, observed at this location. So they're all going to superimpose here and polarize the atom. We're going to see that even though it's an infinite array, only so many nearest neighbors are going to contribute to that local electric field. Anyway, all right. Okay, so the local electric field is E external plus E interaction. They call it the interaction field. All right. The field due to an electric dipole. One electric dipole can be calculated like this. This formula comes from your favorite book. You guys probably, it's a book that physicists use. It's called Jackson Classical Electrodynamics, I believe. But anyway, I was going to put the derivation here, but we'll study that more next semester. Anyway, this is the electric field due to a dipole of dipole moment P, right? This is the r hat unit vector of observation direction. P is the dipole moment. It's a vector quantity. In this case, it's got a y hat component only, plus the table that we derived. Okay, so P is, it's a vector quantity, all right? Okay, and E minus JQ over R and so forth, right? Okay, so you can calculate the electric field due to a dipole using this formula. So what can we do? We could try summing the field due to all the dipoles in the infinite array observed at the location of the particle of interest. So this dipole, we could use this formula to calculate what the field due to this dipole is at this location, observed here. This dipole observed here. This dipole observed here. Sum them all together, right? However, this summation doesn't converge, as the fields we see decay as 1 over r, right? This thing is infinitesimal, right? It's a small dipole, so the far field, you're pretty much in it at lambda by 5 or even 1 wavelength. So the summation doesn't converge as the fields decay proportional to 1 over r, but the number of dipoles. So if I take a circle like this, right? If I take a circle of radius r, and I calculate the field due to all those dipoles at the location of interest within the circle of radius r. We're going to do that in the next slide. And then I increase the radius r, then what's going to happen? More dipoles are going to be picked up, but more dipoles picked up is proportional to r, and the field decays as 1 over r, so the thing oscillates indefinitely. And it never converges. We'll show that, all right? Okay, so to get around this, one can represent the array of discrete particles as a continuous sheet of polarization density. So instead of doing a discrete summation, which we will do, we can model the entire metasurface as a homogenized sheet of polarization density. What did we do when we studied dielectrics? When we studied dielectrics, we said each metaatom polarizes and it contributes an electric dipole, right? And the field due to the electric dipoles altogether, we had to sum all the electric dipoles somewhere, right? That's kind of what we were trying to do in the last slide. However, instead of doing that, we defined the polarization field P as the average number of dipole moments per unit volume. We averaged it throughout the volume, right? And we defined capital P, the polarization field, as the number of dipole moments per unit volume, which is essentially taking an average and defining a new continuous function, right? And by utilizing that field P, we were able to calculate the field due to all the dipoles and therefore the permittivity of the material. Remember? Do the same thing here. Take all these discrete dipoles and average them and define a new P, capital P, polarization P, but it's a surface polarization because it's only a two-dimensional material. And we're going to average them all. We're going to calculate the field due to the average polarization current. And that should be equivalent to calculating the field due to summing discretely all of the dipoles, right? All right, same strategy. So how do we do that? The dipole moment per unit area, or the dipole density, is P sub S, which is equal to P over A squared. Then we can define a surface current density as J omega PS tangential. It has to be the tangential components of this polarization P, right? Or P sub S. So J omega PS is equal to JS, surface current. All right. The field due to the continuous sheet of polarization density can be found as this is almost the same formula as the discrete dipole, the field due to one dipole, but now we're integrating, and we're going to do this throughout a region R greater than R. So what are we doing? We're taking this metasurface of a bunch of discrete polarizable inclusions, subwavelength spaced, and we're going to break it into two regions, one of radius R, a circle of radius R. We're going to do discrete summation of dipole fields within the circle of radius R, excluding the element of interest. And we're going to add to that everything outside of the radius R. We're going to homogenize and model it as a homogenized sheet of polarization density P and M in general. All right. All right. So to find the field due to the homogenized sheet, we have to integrate R greater than R. So it's a sheet with a hole in it, a punctured sheet. And this just becomes PS now instead of P, polarization density, right? And we integrate it. All right. Okay. So what are we going to do to calculate this integral? We're going to introduce a polar coordinate system where the angle phi is measured from the direction of PS tangential, right? So PS tangential is in the y direction, right? So let's say this is x, this is y. Then PS has only a y-directed component. And we're going to define a coordinate system like this, where the angle phi is measured with respect to, well, it's probably the other way, right? Positive is counterclockwise. All right. Okay, so if you do that, transform to polar variables, then you can solve this integral pretty easily, because by setting up that coordinate system, we only have one non-zero component of this integration of the sheet electric field, and it's parallel to PS. And the result of that integration, here's the transformation into polar coordinates. The result of that integration is here. All right. Minus j omega PS, 8 over 4, 1 minus 1 over j k r, e to the minus j k r. And we recognize j omega p as j, right? I'm not sure what happened to this minus sign. I don't know if that's an error. I'll have to check that. All right. Good. So everybody understand what we're doing? Instead of doing an infinite summation, which we'll do later anyway, so this is kind of like an approximate model, we're going to do the same thing we did in modeling dielectric materials. We're going to homogenize everything, define an average polarization field of the dipole moment density, P, and we're going to find the fields due to P at the location of interest, which is the center of this hole. And outside of radius R, we don't know what R is yet. We're going to use the sheet model. Inside the radius R, where things are a little bit closer, we're going to use discrete dipole sum. All right, let's do that. Okay, so what we're going to do to the slides after this one is we're going to prove the statement that we're going to conjecture at the top of the slide. It can be shown that the radius R can be made small enough so that no discrete dipoles remain. So that radius R is going to converge, and it's going to be smaller than the unit cell itself, less than A. All right? Therefore, we don't have to do discrete summation. We just have this integration of the homogenized polarization sheet. Okay, but we'll show how we can prove that. Okay, so the value for that radius R, we're gonna call R naught, which is equal to A over 1.438. It's less than A, right? To show this, let's first examine some limiting cases. All right, so let's first look at the sheet polarization current or the fields due to the homogenized sheet of polarization density. And let's let R go to 0. If R goes to 0, then KR can be considered small. Then we can use the Taylor series expansion of the exponential. And we get the following. The Taylor series expansion of an exponential like this when KR goes to 0, or when KR is considered small, is 1 minus JKR e to the minus JKR plus the higher order terms, right? Okay. So let's plug that in here. We get, here. This is the formula, right? E sheet. Then we plug in the Taylor series expansion for the exponential function. Oh no, we did that here. So here's the Taylor series expansion for the exponential function. Multiply all this out, we get this expression here, right? All right. So E sheet when R goes to 0, is the following. So we've continued that here. And what we get is this expression here at the end. So we have two terms. The first one, this term is easy to recognize, eta over 2 Js, right? This is a plane wave that's generated by a uniform sheet of current. So if you take a uniform infinite sheet of current, a current sheet that exists at some, say like this. And this has current that's uniform, constant throughout the sheet. It's a two-dimensional sheet and it's infinite. And you find the field radiated by that current sheet. What you'll find is it radiates a plane wave in either direction, same plane wave in both directions. And the strength of that plane wave is eta j over 2. All right. So that is a plane wave generated by a uniform current sheet. This other term, the reactive part, goes to infinity when R goes to 0. And that's because the sources get closer and closer to the observation point. It's singular, right? So we expect this kind of singularity in the imaginary part. So the imaginary part blows up. Okay. So that makes sense. It's intuitive. When R goes to infinity and we include some losses, then E sheet will go to 0. R going to infinity means that the fields must go to 0, right? The sheet is no longer there. The radius R goes out to infinity, then it's just a giant infinite sized hole with no sheet. So we expect there to be no field radiated by it. All right? Okay. In the case of lossless background media, the absolute value of the field oscillates as a function of R, and the amplitudes do not decrease with increasing R. All right, we'll see that next slide. All right. So now, to find the local field, we must sum the contribution to the interaction field from the discrete dipoles. We call that E hole, right? E hole was this one. E hole is this one. To the fields due to this polarization sheet, right? Okay, so E local then is E external, the incident field, plus the interaction field. The interaction field is E sheet plus E hole. All right, good. All right, let's look at that in a little more detail. We have E external equal to E naught. E external is equal to E naught e to the jkz. We're assuming it's traveling along the minus z axis. E sheet, we calculated before as a function of R, and E hole is going to be a discrete summation of dipole fields, and the dipole formula is up there, right? So what I did is I plotted this in MATLAB, plotted these three as a function of R normalized to A, all right? And I plotted what's called the interaction constant. It's a dimensionless quantity. We're going to define this more in detail in the next few slides. But beta here is defined as the electric field E of any of these three types, hole, sheet, or interaction, multiplied by epsilon naught A cubed over P. All right, it's a way to normalize it. All right, what are we looking at here? We have first E hole, right, or beta hole, which is E hole multiplied by these coefficients, normalization constants. Beta hole is that function up there, and it's equal to 0 until the radius is a certain value, right? Why do you think that is? Why do you think that the whole electric field is 0 at first until the radius is at least, 1 or 2a? Remember, this is E hole here. This one. If I start off with a radius equal to 0, how many dipoles are in there? 0. The dipole at the origin is excluded, right? 0. Now, as I increase R to maybe A, still there's no dipoles in there because the one at the origin is excluded. It's not till R is, a certain value, a little bit over A, where you start to see any dipoles, right? So that makes sense for this part of beta hole right here, right? Okay. And then it's an oscillating function of R, just like we said. As the radius increases, more and more dipoles are picked up. So the field increases in strength because it's a summation of more dipoles. The number of dipoles that you're adding into the sum increases proportional to the area of the circle. which is proportional to R, right? Or the perimeter, I suppose. Yeah. And the fields themselves decay as 1 over R, right? Okay. So it oscillates, right? The field starts to converge a little, but then you add more dipoles and the field increases in strength, then you increase the R, so forth, right? Now, this electric field due to the sheet is the blue curve, and we see it's singular when R goes to 0, just as we surmised on the last slide, right? It has to go to, why is the real part singular? Okay. I want to look back at this. I just made these yesterday, but what we determined on the last slide is the imaginary part singular, right? Not the real part. Maybe there's an error in my code. Let me go look at it. But anyway, one of these components is singular, right? And it oscillates as well as a function of R. So as I increase R, the field due to the polarization sheet oscillates. However, they oscillate out of phase, yeah? So their superposition, E sheet plus E hole, which is E interaction, tends to some kind of limiting value. Remember, we couldn't do that by a discrete direct summation. It oscillated, right? That's this E hole, the red curve. By adding the homogenized sheet and adding the two, then we can get some kind of converged result. After so many, if R includes so many dipoles, right? But this just shows you that that model converges to some value. It doesn't say what R should be, all right? So we'll calculate exactly what R should be. There's a particular R. We just defined it as A over 1.438. All right, okay, so since there's no loss in the background medium, the field due to the discrete summation of dipoles within the whole radius R oscillates indefinitely as we surmised. The field due to the homogenized polarization density also oscillates indefinitely as we surmised. However, the two fields oscillate out of phase and hence their summation will converge. We see that at a whole radius 20A or so, we obtain a more or less converged interaction field. This indicates that it is only the few nearest neighbors in an infinite array that contribute to the local field, not all of the infinite number of them, right? If I increase R, then I don't change the result much after a certain value. Thus, if the grid is not infinite or not planar, or even the incident field is not uniform, the results for the interaction field of an infinite uniform planar array can still hold. Okay, so that's the only conclusion you should draw from that. Only the nearest neighbors in an infinite array contribute to the local field. All right? Okay, here's some code to make those plots. I could probably check this code and see why. I'll do that. All right, so let's look at what we're going to call the interaction constant in a little more detail. We're almost getting to where we have this model built up, all right? All right. Now we got to go back in and show that our magic radius is A over 1.438. How are we going to do that? All right. Let's assume that R is equal to R naught over 1.438. We'll derive it. But then E local is E external plus E interaction equals to E external plus E sheet only now, because E whole is 0. And we can say E sheet then is going to be equal to beta times P. Why can it be beta times P? Each of the dipoles in the array are infinite and uniform, right? The fields they radiate are proportional to P, but P is the same for all of the elements. So if I add up all the fields due to all the elements, I can factor out that P, because it's common to all the terms. Fields radiated to all dipoles. I wish I had some water. Anyhow, so if I factor out that P, everything that remains inside we call beta, which is the interaction constant. That's what we need to calculate for this model, for metasurfaces made of different geometries. We need to know the interaction constant and the dipole moment. Then we can calculate E sheet or interaction immediately by knowing beta. So everything comes down to beta. All right, so beta is like that, right? We've defined an interaction constant beta, which when multiplied by P gives the field due to the infinite array of neighbors at the location of interest. All right, the interaction constant can be calculated by a direct infinite summation. So, okay, there's a book called Field Theory of Guided Waves by Collins. And this book has a chapter called Artificial Dielectrics. And in that chapter, he does do it does a summation of an infinite number of dipoles using a Poisson sum formula, all right? So somebody, in particular Colin, has considered an infinite planar array of y-directed dipoles and has calculated the sum, the exact sum, due to the infinite summation of dipoles at the location, at the origin, right? Yes.
Why do we compute the infinite array? You say in the previous slide that only the nearest.
Good, yeah. So it's a great point. The previous model that we developed is it's an approximate model. We're going to show that it's very accurate, but it's an approximate model. We resorted to this homogenized sheet current. Why? Because we had the problem of the infinite summation or the number of dipole fields oscillating, right? So we wanted to kind of counteract that by defining this homogenized sheet. By adding the two together, we get some converged result for interaction fields. But that was a function of R, and we don't know what R is yet. We're going to find R. You can do this infinite summation, right? This infinite summation is done, but this is for y-directed dipoles. To do this for all the other orientation, the magnetoelectric and all that would be cumbersome. So that the model that we're developing, which is based on the homogenization, is easily applicable to all the other cases. So it's a good model, and we'll show that it's very accurate. Yeah, so when I first started to read through this, I was like, well, if we have a formula for the direct summation, then why do we need the approximate model based on homogenization, right? But it allows us to do much more than this model does. Yeah, maybe. Let me get a sip. That'd be great. Thank you. Sorry. Yeah, I appreciate that. That's good. All right, thank you very much. So yeah, that's the strategy. So the interaction constant. But look at this formula, right? It's pretty intractable. I guess you can solve it, right? But it's a pretty crazy formula. So here, this formula is broken into two parts. The first one is called the static, when k goes to 0, the static interaction constant, all right? So when the frequency goes to 0, you get, this thing can be considered like an array of static dipoles, and there you can calculate what the interaction constant is in this closed form here, all right? Then there's this dynamic one where it's time varying dipoles, and the time varying dipole formula is here. So it's a pretty long formula. This can be summed in the same way that this one was, using the Poisson summation formula. And I'm going to work on that, but I didn't put it in this presentation. But that thing can also put in a little nicer form where you can do these infinite summations in a closed form. All right? Okay. So how are we going to use this exact result to calibrate our model, our approximate model based on homogenized sheets and the whole of radius r, right? Well, we're going to use it to determine what r is, the degree of freedom. If we match the exact formula with our approximate formula or approximate model, we can find what that radius r should be so that we get the exact result. At least it will give us pretty good results for the dynamic out until pretty large spacings, right? It's Ka. So the parameter we'll see is Ka. Ka, which is 2 pi over lambda multiplied by the spacing A. So this product here is the parameter of interest. That parameter, I think you can go out to like 3, K equal to 3. So you can either change the frequency or change the spacing. And you can go up to 3 for that product. And our approximate model will equal the exact model, the exact calculation. Outside of that range, it is not a good approximation anymore. All right. So this model was developed by Treyakov, the previous one, this calculation done by Colin. So you can look into that. So what have I done on the next slide? We're going to determine what R should be in order for us to get at least the static first, right? We're going to use the static result to find what the R should be. All right. So we can compare the exact interaction constant with our approximate derived one. First, let's normalize them to be dimensionless. So we take this beta approximate that we have, and we have to write it in terms of a function of Ka and normalized, all right? So take beta approximate, the way we have it, E sheet over P, right? that's equal to minus j omega 8 over a squared 4 into 1 minus 1 over jk r naught, either minus jk r naught, right? It shouldn't be r naught yet, it should be r. We're gonna determine what r equal to r naught. We're gonna write this as beta approximate bar, which is now normalized, the normalized interaction constant, which is e sheet epsilon naught a cubed over p. So we've multiplied by epsilon naught a cubed, and we get this result. Then we're gonna write this in, once you look at this, after normalizing it, it's a function of Ka. We divided r by a and introduced another a here, and same in the exponential. So what we have here is a function of Ka, right? All right. Do the same thing with the static interaction constant. Take this formula, we normalize it to get beta bar by multiplying by a cubed. And because of the way that this was derived in Collins' book, it's only a cubed. We get this formula here, all right? To make it dimensionless, a dimensionless interaction constant. That is also, or that's a constant value, right? The static value. It's really only valid at Ka equal to 0. It's the static value. Now, what you can do then is, let's equate the two. Let's take the real part of our approximate model and equate it to the static value of the exact interaction constant. If you do that, take the real part of our approximate model here, you'll see that the j's cancel. So minus j into 1, that's imaginary. So then it's the second term. So minus and minus become plus. J's cancel, Ka's cancel. We get 1 over 4r over a, which is a over 4r, right? A over 4r. We're calling this r naught because it's static. And that's equal to our static interaction constant from the exact summation. So if we solve this equation here, this is the modified Bessel function. I think I said that on the last slide. Modified Bessel function of the second kind. We studied those earlier in the course. We get r naught equal to a over 4 into 1.2 into this thing, right? Into the static interaction constant. And if you calculate this is just a pure number, then you get a over 1.438. So if we have a radius r of a over 1.438 in our sheet, which is our homogenized model of the metasurface, then we get the correct value for the static interaction constant. All right. Later, I'm going to plot. Okay, so here, what am I plotting? The blue curve is the real part of our approximate model as a function of Ka. It's a plot of this function here. And the red curve is the imaginary part of that model right there. The yellow curve is this static value plotted as a constant. And what we see is, okay, so these blue and red plots of this approximate model are not equal to a over 1.438. All right, we see we get the correct static value, which we should for the real part, right? Now, if I were to plot, which I'm going to do, but if I were to plot this thing, the exact dynamic as a function of Ka, I just didn't have time to do that, but if I did, then you would see that the curves almost overlap this whole thing for the whole domain of this curve. They'd be like this, right? The exact dynamic. So what that says is r equal to r naught, which is a over 1.438, gives you the correct interaction constant. The homogenized sheet is exactly the same as a discrete summation of an infinite number of dipoles. If we choose this radius, a over 1.438, for range of Ka going to about 3, maybe 2, 2.5, 3. All right. So that means we can find the interaction field using this function by this function alone, right? That's great. That multiplied by p. Yeah. The dipole moment. Okay, good. So now let's use that information and calculate some reflection and transmission coefficients from the metasurface made of those little anchor dipoles, right? All right. So since the metasurface consists of subwavelength particles and they're subwavelength spaced, and it's an infinite extent, the reflective field is a plane wave. Let's first consider excitation by a normally incident plane wave. In this case, the total electric field in the plane of the dipole is E total equal to E external plus E scattered, right? E total equal to E incident plus E scattered. And that's E external minus 8 over 2 JS. The scattered field, which should not have two C's, but the scattered field itself is a plane wave. And we know that a plane wave is generated from this current density, JS. Minus 8 JS over 2 is the scattered field in terms of plane waves for normal illumination of an infinite array of subwavelength space particles, yeah? All right. We can express the external field, E external, in terms of alpha, beta, and Js, all right? Alpha, the polarizability, beta, the interaction constant, and Js. So this lecture is going to really help you guys if you ever pick up a paper and read about metasurfaces and the models that are used to describe them. All of this is going to be in the paper. The derived results, the final results, especially anything you read with Tretyakov. That's the author. All right. So E local is P over alpha, right? Because P is equal to alpha E local. We're saying that E local is also equal to E external plus beta P, right? We derived that before. So now P is equal to alpha E external by solving this equality, alpha E external plus alpha beta P, right? All right. Now we can move this term to the other side and factor out the P, and we get 1 minus alpha beta into P is equal to alpha in E external. Now we can solve for P as P equal to alpha over 1 minus alpha beta in the E external. So we've now written the dipole moment in terms of the illuminating field and the polarizability and the interaction constants. Good. So let's go now to the definition of the current, which is J is equal to J omega P tangential divided by A squared, right? J omega capital P, but P is number of dipole moments tangential divided by A squared for the dipole density that's related to the surface current. All right. So we know what P tangential is now. We can substitute it with this, and we get J omega over A squared alpha over 1 minus alpha beta E external. And we can solve for E external as alpha squared or A squared over J omega 1 minus alpha beta over alpha into JS, right? We can rewrite this as two separate terms and we get that, yeah? Okay, why do we do that? We've written E external in terms of J. Now we can plug this into this formula here. We have E external and in terms of J and 8 over 2 in terms of J. We can factor out a J. Why does that help us? Because then we have something multiplied by J is equal to E total. And I don't know if you guys remember, but that's a boundary condition, an impedance boundary condition. E equal to eta times J, or E equal to Z times J. E total equal to eta sheet times J. So we can define a surface impedance for this structure now, this metasurface. E total is equal to E external minus 8 over 2J. We've written E external in terms of J as well. Now we can factor out the common J, and we get this, all this left inside of the brackets. All that has to be the surface impedance because the boundary condition E total equal to Z into J is the impedance boundary condition, right? The impedance is the proportionality constant that links the total electric field to the induced surface currents. Good. So now we have a ZS. Once we have a ZS, we have our boundary condition that we need because J is equal to the tangential discontinuity in H across the metasurface, and that's equal to, so take this ZS and divide both sides by it, and 1 over Z is Y. The admittance, sheet admittance multiplied by the total electric field. It could either be the plus or the minus sign. Really, this is E average, okay? But E average is equal to, because of the first boundary condition here, it supports no magnetic current, right? It only supports an electric current. If the boundary condition or the metasurface supports only electric current, then the magnetic current is equal to 0. Then that means that you can have no discontinuity in tangential E when you go through the metasurface because there's no magnetic current. And in order to support a tangential discontinuity E, a magnetic current must be present, magnetic surface current. That means tangential E is the same on both sides. Now, E tangential average is equal to E1 or E plus E minus divided by 2. But if E plus and E minus are the same because the metasurface does not support magnetic surface currents, then this is nothing but 2E plus divided by 2, which is just E plus, or 2E minus divided by 2, which is just E minus. So you can write this right-hand side like that. All right, good. Let's calculate some reflection coefficients and we're done modeling that metasurface. So let's assume the metasurface here is in the XY plane. It's infinite. The Z direction is normal to it. We have an incident plane wave in medium 1, which has impedance eta naught. And we have a transmitted medium, which is medium 2. It also has impedance eta naught. And the illumination is normally incident, like we've been talking about this whole time. But now this metasurface is made from a bunch of those anchor dipoles that we had in the first few slides. All right. So the incident field, E1 incident, is that E1 plus equal to E1 plus X hat, yeah? All right, so that's this field. And the reflected field here is gamma times E incident. The transmitted field here is tau transmission coefficient times E1 incident, yeah? Okay, because these are all plane waves, we can easily find the magnetic fields associated with each of those electric fields by doing 1 over eta R cross with E, right? And we get these plane wave fields for the magnetic fields. All right, now we go to our boundary condition. N cross H2 minus H1 is Y into E, right? Or Y into E2, or Y into E tangential average, which is this. All right, great. Let's substitute in all of our fields. H2, what is H2? Well, it only is H2 plus, so we put H2 plus here, which is this formula. Then we have minus H1, which is H1 incident plus H1 reflected. So here's minus H1 incident, here's minus H1 reflected with a gamma. All right. The right-hand side is YS into E tangential average. All right, so that's YS over 2, the 2 comes out. And then we have ET1 plus ET2. E incident plus E reflected is ET1 plus tau E1 is E transmitted, all right? So if you solve, okay, so here we have a bunch of X hats and here we have Z cross with Y, that gives you minus X hat. So everything is X hat. We drop all the X hats, we have equation 1 here, all right? Do the same thing with the other boundary condition for the magnetic current, which is 0. So we have E2, which is tau E1 plus, minus E1, which is E incident plus E reflected. That's all equal to 0. And we can do the cross product and determine that Z cross with X is Y. And we could drop the Y's everywhere, the Y hats, and we have equation 2. Solve both of these equations. These are 2 equations and 2 unknowns. The 2 unknowns are gamma and tau. Gamma, tau, everything else is known. Yeah, it's all E1 plus now. We know the incident field and we know eta naught, tau, gamma. If you look, it's all in terms of E1 plus. Known, right? Solve for tau, solve for gamma, we get these 2 expressions. These are well-known expressions here. Transmission reflection coefficient of a metasurface with impedance ZS. And we know what the surface impedance is, ZS, because we derived that on the last slide in terms of the interaction constant and polarizability of the meta atoms making up the metasurface. So now we've finished it, right? We have the full model. We calculated alpha, we extracted it from FACO and used our spherical mode expansion equality. Beta, we calculated as the field due to the infinite homogenized polarization of the sheet polarization density. Sheet of polarization density, yeah? And we proved that the radius should be R equal to A over 1.438, and it's only due to the sheet. So we know how to calculate beta, we know how to calculate alpha, eta we know, but there's eta naught as well. And then A squared, so we can calculate the reflection and transmission from this. Okay, so it's an easy problem, right? Only electric surface current, only vertical dipoles, only illuminate with a plane wave, normally incident, it's an infinite array. But that took some effort to get to this, right? We had to take a whole lecture to do it. But we can now calculate the response of that metasurface. So what can you do with this, right? It only has an electric response, so there's not too much we can do. We have a few degrees of freedom. We can control the reflection or the transmission phase or amp or phase probably, right? But because it's passive and lossless. We haven't restricted ourselves to that, but assuming it's passive and lossless, then we can either control the transmission phase angle, but we can't do anything about the reflection. It can't be matched, right? If we add the magnetic dipole moments now, change our meta atoms to support electric and magnetic dipole moments, then we'll have an additional degree of freedom, and we can control the transmission phase and make it reflectionless for the same impedance on both sides and normal instance like this, right? Then we can design a metasurface to give us a particular transmission phase delay and impedance match it to the incident medium so that everything goes through with a phase delay. So all of that is coming up in a book chapter that is coming out early next year that I published in a book by, it's edited by Alu and some others. But look for it next year. It's called Metamaterials by Design. And if you want to dig into more of these, you know, adding degrees of freedom and making metasurfaces out of electric and magnetic dipoles or even bisotropic and integral equation modeling of metasurfaces, you can look at that book chapter, which will be out early next year. Metamaterials by Design, edited by Andrea Alou and some others. Okay. All right. What else do we have? Okay, so yeah, then we get into a little bit more complex models, including bioanisotropy and so forth. If you're interested in the subject, then consider joining my research group if you already don't have an advisor. And you can always come to my office and talk about it as well. Or you can come to the next semester's course, ECE 5106, where we're going to dig into all of this and numerical methods and geometrical theory of diffraction and method of moments and waveguides and so forth. All right. So it was a pleasure having you guys this semester. I really had fun teaching the course. Please fill out the spot evaluations. I look, there's only like half of them done. I need those. So fill them out. And I will see you guys next semester, hopefully, and around campus. All right. And for the final, I'll send an announcement tonight that'll tell you what to study in particular, but don't take just that for it, right? Study everything you normally would, but focus on these two topics. All right. All right. Have a good one. Oh, there's homeworks here if you guys want it. Homework 5 returned. Yes? Yes, go ahead. All right. Very good. You're doing very well in this class. You were worried in the beginning, right?
Yeah, I was. I'm putting a lot of work into it.
Yeah.
I think it's very well.
Very good. Yeah, I'm glad to see you're definitely doing well.
Thank you.
Good.
I already submit the project.
Oh yeah, I can't wait to read it, man. That's cool. So you got everything to work.
Yeah.
Very good.
Yeah, it's fine.
Was that? Yeah, very good. Yeah, for sure. Yeah, for sure. Okay, yeah, so you already turned in the form, the audit up? Yeah. All right. Yeah, well, audit next semester, that's totally fine. Yeah. All right, man. Yeah.
This one, this place I will be gone for a bit of this place. Sitting in the middle there, you don't know what when people stay behind you, then will you use your laptop? Yeah, you just open your slides. So from slide 5 to 11. Yeah, use version 2. Yes, the yeah, so they have been Wi-Fi, right? issue with the calculation. Last time I did it in a wrong way, the matrix calculation. But I was doing the wrong way, the multiplications. So last time I had to do all the matrix multiplications manually. Because this was giving dimension error, then I found